Here you see three different graphs. What I'm plotting on the x-axis is the neighbor's influence. On the y-axis is node i's state. This is node i's state, and this is neighbor's influence. The first graph is actually for random walk model that we will talk more about in this lecture's advanced material part of the video. This and this graph are depicting contagion and infection respectively. For contagion, there is a certain threshold above which you flip. So it's a binary state. And for infection here, however, we're going to see that impact of topology can be modeled by looking at your neighbor's influence on your state in a probabilistic way with a certain slope, which is beta Si. So in particular, when we look at a given graph of connectedness with associated adjacency matrix A, then we can write down the infection influence model's dynamics through a different set of differential equations, incorporating this adjacency matrix. Let's take the simple SI model. Okay. Then, for node I, it's not the general global population percentage anymore. It is the probability that node I is in the state of being susceptible at time t. So we have to interpret this as the probability that node I is in state S. And that probability evolve over time with minus b beta, okay, times the summation of all the neighbors. Let's assume this is a bidirectional graph. So aij equals aji. That could be 0 or 1 depending whether j is neighbor of I or not. If it's 0, the rest of the term doesn't matter. If it's 1, then we look at what would happen. It will be Si times ij of t. Again, I here is the state of the probability that node j finds itself in the state of being infected. Si is the probability that node I finds itself in the state of being susceptible at time t. Okay, we can also write down di for node I dt, but that would be just minus the above for the simple SI model. So let's just focus on this expression here. This expression is in fact incorrect. Okay. It's wrong because we cannot actually write this down as such. What we actually need to write down in English, okay, is the following. Is to write down this as one single entity is the joint probability, okay, that node I is in the state of S and node J in the state of I. Okay, and what will that probability be? Then we need to know the probability that some neighbor of node J, other than node I itself, got to the current state of infected, got to the current state by being infected and then making node J infected. So we have to look at all the neighbors of node J that induces this joint probability of node ij in this state. But in order to do that, we have to look at each of these neighbors and the trajectory of the state transition in the past that have led to this state. As you can see, this quickly gets out of hand, is no longer tractable. So what we're actually doing is to stop this propagation, tracing back, and say, let's approximate. One standard way to approximate out of several that we mentioned in the textbook is the order-based approximation. The first order approximation actually says, well, let's just pretend that this joint probability can be written as the following memoryless decomposed product of two individual probabilities. This is actually an approximation. But having written down this approximation, then we can say, well, this SI is not dependent on J, so we can pull this out of the equation and start doing approximation. So let's do that approximation here. Let's write down, for example, dii at time t and its rate of change with respect to t is beta, okay, times si of t after this first order approximation and pulling si out of the summation over j times the summation of aij times ij of t. Now this is s is just 1 minus I by definition. And now we have to make yet another approximation to say that during the early time of infection, the percentage of the probability you find yourself infected is very small, so we'll approximate this by erasing this part. And now we can write this down as a vector equation. Write the probability of each node may find itself in the infected state at time t as I. This is not identity matrix in this lecture. Okay, it's just a vector of these entries stacked up equals beta times the matrix A, adjacency matrix, times this vector at time t. This is almost the exact same as before, the scalar evolution, except now it's a vector evolution with a weighting by this adjacency matrix A representing the topology's impact. Again, we can apply the trick to represent this vector as a weighted sum of the eigenvectors of the adjacency matrix as before. Skipping the derivation, we see that the solution of this vector of probabilities is the summation of some weighting factor, doesn't matter, times e to the beta lambda k times t times vk. These vk's are the eigenvectors of the adjacency matrix A of this given graph indexed by k, and this summation by k, and is weighted by this exponential factor e to the beta. Beta is the given disease spreading rate times the current time t times the corresponding eigenvalue. So as time goes on, the largest eigenvalue will dominate effect. And that's going back to our old story again. Okay. Now, I want to end this model, and therefore actually this lecture and the sequence of 2 lectures on influence model with a case study on the disease of measles. Okay. Measles is an infectious disease that causes about 1 million deaths worldwide each year, but in developed countries, the population is sufficiently vaccinated. It affects very few people. It achieves what's called a herding immunity. That says that there's enough immunized population that the infection will not cause a pandemic. What is a herd immunity then? So we want S of 0 at initialization time sigma to be less than 1 to prevent the infected population from flaring up. That means we need S of 0 less than 1 over sigma. That means we need the initial recovered, presumably through vaccination program, population percentage being bigger than 1 minus 1 over sigma. For measles, people have estimated from previous outbreaks of the infection that the sigma is very big. It's about 16.67. That means we need this initial vaccinated rate to be 94%, which is big but not that close to 100%. Now, however, the vaccination is not always effective. It's only about 95% effective. So that translates, we actually need the vaccination rate to be 99% in order to achieve herd immunity, to achieve this condition. So back in 1963 in the US, the measles population started drop because of the introduction of the measles vaccination. but then it still stayed around 50,000 people every year. In 1978, the US government tried to make the immunization coverage wider to eliminate measles, but it dropped to about 5,000, but stayed around there. In fact, sometimes it went up to 15,000. So just increasing the coverage of immunization didn't help. In 1989, US government introduced the 2-dosage program. So you have to get 1 dosage when you're around 1 year old, another around 5 years old before you go to school, a public place all the time. And this time, the 2-dosage program, which is much more expensive than the single dosage program, was able to achieve the vaccination rate 99% needed to counter this large sigma of 16.65 for measles in order to satisfy this condition and thereby achieving herd immunity. And indeed, since then, the number of reported cases of measles dropped to under 100 within a few years' time. This is a very interesting story showing the power of the particular differential equation model we just developed for infection. Now, we have touched upon 4 influence models together with 3 more in advanced material part of these 2 lectures videos. Altogether 7 influence models. Which one to use is an art, and there's a big gap between theory and practice. But some take-home messages offer insights. For example, different ways to think about and quantify the importance of nodes and links. Okay. For example, in today's lecture, the contagion model and the optimal seeding being a difficult problem, and the infection model that we just talked about, how differential equation model the change of states allow us to make some prediction and very useful public policies. So with that, we finish the influence model part of the lecture, and we move on to the topology reverse engineering part. So see you in the next lecture.